Hello everyone, we are starting a free open lecture in our Discord. All our lectures are held weekly, without interruptions. If you, the viewer, want to ask questions and receive answers in an online format, join our lectures. You can find the link to Discord in our Telegram channel. To find out the time of the lecture, please join our Telegram channel and stay tuned. Accordingly, let's get started. The problem is specifically called minimization of the sum, with a time limit of 2 seconds and a memory limit of 256 megabits. Well, let me just go ahead and give you a detailed description of exactly what I have carefully prepared for you. We will have constraints ranging from 1 to approximately 3 multiplied by 10 to the power of 5. Moreover, the tests are indicated there, but they can be disregarded because it is a total, as usual, from 3 to 10 to the power of 5. K ranges from 0 to 10. Array A of n distinct elements, where each element is from 1 to 10. 9. Accordingly, the conditions of the problem here are to simplify everything that is unnecessary. It's quite short. We have an array A of n elements, and we have the following operation on it, where each operation consists of selecting any element AI and replacing it with a neighboring element of the array. This can be either at I1 or at I plus 1. Accordingly, our task is to minimize the sum of the elements in the entire array. That is, we have vibrations, we perform them, and in the end, it should be as small as possible. A smaller sum for the entire array, clear conditions on what we need to find, what is given to us, and what we can do. So, there is a small example here in essence. In this scenario, we are given that the value of n is specifically equal to 6, and we have k operations being performed on the array C4. The question is, how can we, in the most optimal way possible, so to speak, cut or modify this array? To begin with, we need to carefully and precisely alter the number from 4 to a single one. This step is crucial. Initially, we have the number 2 appearing in the third position of our sequence, and we need to modify it to become a 1. Following this adjustment, we proceed to alter the number 4, which is currently in our sequence, and change it to a 2.
Want to become a great programmer? Subscribe to our Telegram channel.
And in the end, we change that 2, with which we remove the 4, to a 1 as well. After considering all the factors and calculations, the final answer that we have arrived at is the number 9. In other words, what we are observing here is that we have the ability to substitute those specific elements that were utilized earlier, and what we can see is that we can replace those elements that we used earlier,
replace them with the elements that were slowed down before. That is indeed this one here. It actually came from almost the other end of the array. And thanks to these observations, we will have a comprehensive solution in general, with additional insights. Accordingly, the first fact that can be seen here is the constraint. We have a constraint of 10 to the power of 5. Oh, and how many tens? The time limit is approximately 2 seconds. This means we have n multiplied by k, raised to a power. It can either be done in OK time, but it's unlikely that such a solution exists, here, or in OK squared, or in OK cubed. I found a solution with a complexity of k cubed, but I will look at the analysis later. It can also be done with a complexity of k squared. The solutions themselves are therefore theoretically different, but we actually finished 10, so it doesn't really matter. Also, our DP, dynamic programming plane, will have a second coordinate, and the first coordinate will be enumerating the first elements of the sequence, while the second coordinate will be g. This is the enumeration of the number of modified elements. That is, we have this. And after that, we can identify some subtask. For the first elements, we have modified the elements in this set and obtained some minimum sum. Our goal will be to find that. In other words, we will essentially have a DP, dynamic programming, of nk, where n is the entire array, and k is all the possible operations that we will most likely use, although there is a case when this needs to be optimal. For example, when the entire array initially consists of a single element, There is actually nothing that needs to be done. Let n be given and k equal to 0. Also, what we can notice here is that we have the possibility to replace elements in the array in whole blocks. We replace two elements, which are square units, and this essentially constitutes a block in its entirety. That is, we painted here and here, in this particular area, which resulted in a total block of length 2, completely consisting of ones from this end, and if we allocate this entire block, we actually have ones from the other end. So we will essentially get a block of length 4. With such blocks, we can color pieces of the array.
How to attempt to build TP, TFSP. The first task that I mentioned earlier is the first, E elements. We certainly embrace first of all the E elements, among which the J elements have slowed down. We will iterate over I and J, and we will also try to create a block using each AI element consisting only of elements equal to AI simultaneously. This block, which is designed to be of a specific length, will have a length of G plus 1, where all G elements within this block will be replaced with AI, with the exception of the given element itself. Then we will carefully iterate through the beginning of this block in detail, and how many elements we changed before, step by step. In essence, as the name suggests, it will resemble a diagram. We have a block that starts at a beginning point and ends at a concluding point. Let us consider it as such, with its components and connections clearly outlined. Inside it must definitely indeed necessarily be it. The size of the block is G plus 1. It turns out that where G plus 1 is, it is essentially end minus start plus 1. Here, in this context, everything is specifically replaced with I. That is, in this particular case, we will use cumulative operations here. As a result, therefore, in conclusion, ultimately, in essence, in summary. J. We also know what was before. Before, we had passed the starting middle of the elements. And certainly, some k has indeed been specifically replaced in the range from 0 to k, in particular, without a doubt, without j, because we have already occupied elements in j and we cannot use them here anymore. Here we can have a maximum of k.
And here we have obtained a subtask in this specific context, to which we refer back, as we have previously mentioned. We obtained a value that we will use from our experimental block, which is crucial for our calculations. This value, denoted as g, will be multiplied by the factor we have determined. We add what was before to the existing value and choose the minimum from what we calculated from the previous calculations for dp.ng. In our dynamic programming approach, we select the minimum to ensure optimal results and obtain our answer. Accordingly, the time complexity here will be n multiplied by k cubed, where n is the number of elements and k is a constant factor. In terms of time, it will be n multiplied by k. For instance, if n represents the number of data points and k is a constant related to the algorithm's efficiency, the overall time taken will be significantly influenced by these factors. We, accordingly, will always have this look. We will iterate from 0 to the specified range, ensuring that each step is carefully executed and monitored for accuracy. By oj from 0 to I, iterating start from I, minus j to I, and then we need to take a break on the formula. Step by step, carefully, we will read all of this, and the answer will be like this. Are there any questions about the idea of solving this problem? Well, everything here is quite clear, in principle. Do you want to become a cool programmer?
Want to become a great programmer? Subscribe to our Telegram channel.